Hello everyone, can you hear me?
I can hear you now, ma.
Good morning, ma'am. Can hear you now, ma'am.
All
Good
right,
morning, ma.
good morning everyone. You're welcome to class. We have 32 people on the call. What's going on? You're supposed to be around 58 or 60, thereabouts. Okay, so let's start. Um, I sent your groupings to you. That was observed that some names were repeated while I think there was no omission, but some names were repeated. So I've made necessary corrections. I'm going to send you the updated copy. Though I've been trying to send it, I don't know, my network is messed up this morning. So I don't know what is, it's not delivering to Sabata and what's his name, Jackson. So I don't know why. Uh, okay. So I believe the groupings you have seen, you saw the instructions attached to it. We have 7 groups. I want to make it as the groups to be as compact as possible. I don't want so many people in a group, so possibly um, 8 people in a group. And if you find yourself to be 9, no problem. So you all have your topics. You work on the topics, try to get an industry expert. You see, if you look at the topics I gave to you, you see that they are application related. They are not topics that are theoretical. We want you to look at what is happening presently in industry, okay, the current trends, and then bring out applications, discuss the applications, be able to identify problems that are related to the topics happening in industry. I don't want something you read from the textbook, okay? And why we are doing this is because if it is not possible for probably for you to go on an industrial visit during this course, before this course ends, then you must have had the opportunity to liaise or discuss with an industry expert, someone there in the industry, you know, that is possibly um, into absorption processes or something related to it, who will be able to guide you on what is going on, probably be able to share videos with you, share pictures with you, share ideas with you, so that you'll be able to speak from somebody that is knowledgeable, as per the topic you are given. So just try as much as possible. I'm not saying you shouldn't read papers, read text, read as many materials that at your disposal. But at the same time, um, I'm going to be looking out for the practical aspects of the topic you are discussing. So please work with your group members. Don't work alone. And for those that are, um, you know, that are usually laid back, you think others can do the job, and then you just show up on that day and behave as if you were part of them. Please, that will not work. This is how your presentation is going to go. I can decide to call on anybody to start and then ask him or her to stop at a point and then call on someone else to continue from where he or she stops. So um, apart from the fact that I'll be scoring the group together, I'll also be looking at the contribution of each person, and it will show from your presentation. If you have not participated in the development of whatever you are presenting, it will show why you are presenting. So please don't mess yourself up. Try as much as possible. I believe you have short group meetings. Please try as much as possible to be part of whatever they are doing in your group. It will help you. It will help you, okay? Yeah. So that's about that. So let's just discuss one or two things for today. I have tried as much as possible to see that your topic cover the range of what adsorption is all about. And there is also one of the interesting topic on tech. So those are in that group. Please look at, we are present in the world of tech. So look at how technology can be, applicable in adsorption processes. How are they being carried out presently? Oh, okay. Are there lapses? Are there things they are doing, routinely that can be maybe can be programmed? You can bring in your knowledge of uh, of machine learning, and the likes. So look at how tech can make adsorption processes seamless, and whatever else you can find, that will be fine. Okay, so please, can you see my slide? I don't know what is going on. I just want
Yes, ma'am, I can see it.
okay, that you can hear me and at the same time you can see the slide.
Yes, ma'am.
Okay, light is messed up in my area and network is as well. Um, network is equally misbehaving, so I just hope we're able to stay longer today. So So last week we looked at adsorption process, and then what absorption is, the difference between physical and chemical absorption. Please, I expect that you read. Please read. Don't wait for me. Don't wait. This class is just 2 hours in a week or about an hour plus. If you're having physical class, maybe you know, it could be more effective. I don't know. But I'm just saying that you should try as much as possible to, I can't put everything in the slide. I have notes here. I'll probably maybe screenshot these notes. I think I even have them on LMS. Please check up my page. This course on LMS. I should have them on LMS. So um, though I have the updated version, but you can still check the one on LMS. Check it out, please. So I'll also probably do a copy of this and e-copy and send to you. So because everything cannot be in the slide, especially the calculations, having to type out all these calculations. I know there are other tools that can be used. Maybe we'll try and work around that later as we go on in the course. Okay. So we look at adsorption. We saw single layer adsorption, multi-layer adsorption. We are still going to see more of that when we get to isotherms. But basically today, then, okay, I gave you this quiz. Discuss factors to be considered in the choice of suitable separation process. So I believe you've laid your hands on it. And please, if you can also possibly submit, but maybe your submission will be in this format. You just submit a single word file, maybe each person a page, submit it to your class rep or assistant class rep. So collate it all in a single word file, So everything will be all together. On each page, where you have your assignment, you have the name and your matric number on top. So name and matric number, then your submission per page. Okay. So the next page, name and matric number and whatever you've written, name and matric number, whatever you've written. So just like that. Please don't copy and paste. Don't copy and paste somebody else's work. It's quite easy for me to identify if you copied and paste. So please don't do it. Try as much as possible to read. Okay. So it's for your own good. So I'm trying to put these nuggets together, but this says, okay, before I go on, who can remind us something that I learned from last class? Maybe something you can still remember. Possibly one of the things that still rings in your mind that oh, if they wake you up from sleep, you can still remember this point. Anybody like that? Probably without looking at the slide. Something you can still remember. Yeah, anybody? Can anyone hear me?
No, I can hear you.
Okay.
From the last class, I learned that adsorption is the process whereby the adsorbent is attracted to the surface of the adsorbate. I can't really clarify that now. And it's adhered to the surface as a form of separation process of the particular chemical or compound which the adsorbate is supposed to absorb. Then I learned of single phase, a single layer and multi-layer adsorption. That is where in
Adsorption.
single phase adsorption, thank you. In single phase, the adsorbents are adhering to all the adsorbents adhere to the surface of the adsorbent, while in multi-phase, all the remaining adsorbents that haven't adhered themselves to the face of the adsorbent are stacked upon the the adsorbents that are in direct contact with the adsorbent.
Okay. What's your name? Should be able
Edward
to.
Zivaiman.
Okay, Edward. All right. Thank you very much. That
Hello,
was.
ma. Hello, ma.
Yes, I can hear you.
I learned about adsorbents and absorbents. I learned that adsorbents is simply a surface phenomenon where the adsorbents are being adsorbed on the surface of the adsorbent. And I also learned that they can also be removed by desorption process. And I also learned about absorbent also that it is a bulk fluid phenomenon. Instead of them to be adsorbed on the surface of the absorbents, they are absorbed in them. That's it all, ma.
Okay. Yeah. Anybody else?
Good morning, ma.
Yeah. Good morning.
Can you hear, ma?
Yes, I can hear
Oh,
you.
okay. So
Go on.
I learned that. Okay, I learned that adsorption is a phenomenon where adsorbents adhere to the surface of adsorbent. Most times the adsorbent is solid. And I also learned that I remember the diagram that you showed us where the adsorbate adhere to the surface of the adsorbent, and it also said that desorption takes place when adsorption takes place, like they can occur simultaneously. And desorption is when the adsorbate is leaving the surface of the adsorbent. In that diagram, I also remember that there was adsorptive. Adsorptive are the molecules, um, maybe the fluids that have not adhered to the surface of the adsorbent or are on their way to adhere to the surface of the adsorbent. So adsorptives become adsorbates when they adhere to the surface of the adsorbent.
All right. Fantastic. Well done. Okay, so that will be all. I want to share this. Let's just watch this. Can you see my screen? One night.
Yes,
Yes, ma'am.
ma'am.
Okay. Okay. So I see someone said no sound. Can you hear the sound from the video?
No, ma,
No,
No,
ma'am,
ma.
can't
we
hear
can't
the
hear
No,
sound.
anything.
Okay. So what do we do to that now? Can you hear it now?
No, ma, it's not
No,
No,
sound.
ma'am.
ma.
no, ma.
Structure of these materials is created by a three-dimensional network of interconnected channels and cavities with pore sizes ranging from 3 to 10 angstroms. The size of the pores determines the selectivity of the molecular for specific molecules.
Okay. So no sound, right?
It's
No,
very
ma,
low,
we
very
could
low.
hear you
It's
for a while now.
quite
Ma,
low,
there's no
ma.
sound. There's no sound.
There was sound, but it was faint.
Quite low, ma.
Okay, you could hear me, but you could not hear the sound from the video.
Ma, we could hear the
No,
sound
no,
from the
we could
video,
hear the sound, but it
but
was
it
very
was
low.
very low
It's
and somewhat flagging.
yeah, Zoom is making it the speaker, so that's why we could just let it like kind of whisper also.
Okay. That means I have to change my speaker setting, right? Okay, so what I will just do is to send you the link to watch the video. It's about, I think about 3 minutes, 2 to 3 minutes. So,
Okay,
okay,
ma. Thank you, ma.
all right. So let me just go back to the slide. We'll find a way of, okay, can you see the slide?
Yes, ma'am.
Yes,
We can
ma.
Yes,
see us.
ma.
You can see adsorbent, right?
Yes, ma'am.
Yes,
Okay,
ma.
okay.
Yes, ma'am.
Okay, so I decided to pull up a video for you to see so that you have a practical feel of what adsorbents are. An example of the example of adsorbent that is being discussed in that video is molecular sieve. Molecular sieve. So it's showing the importance of the surface area, the pore size, the particle size, okay, to adsorption process, which is used for. Okay, so here we just want to look at the key properties of adsorbent, your adsorbent. So it has to have a good internal surface area. So it provides the adsorption power, the capacity, and the speed of action of the adsorbent. So depending on what you are trying to, the particles you are trying to adsorb to the surface, you have to consider the size and then the internal surface area of your adsorbent choice. Very important. Then you know that when it comes to surface area, a larger surface area, when you have a larger surface area, you have a more effective adsorption. Okay, so most of the time you have these adsorbents in very tiny, when you have them in tiny particles or tiny sizes or smaller sizes, when you have them in smaller sizes, it offers a larger surface area and a larger internal surface area as well. Okay, so it makes adsorption more effective. Then you have the pore size. So the pore size is chosen based on the size of the particle to be adsorbed. Okay, I wish I have had a picture to illustrate this. So on the size of the particle to be adsorbed, you have to be sure that the pore size can actually accommodate the particle that's to be adsorbed. Okay, depending on the size, whether it's within the range of small particle size, medium particle size, or large particle size. Okay. Then the surface chemistry. This is quite important from the knowledge of your chemistry. You don't want a reaction between your adsorbate and the adsorbent, which will probably lead to maybe synthesis of another material that can hinder your process or cause a disruption in the process flow, or production of maybe other corrosive substances, you know, that can also disrupt the process or lead to corrosion. So you have to understand the chemistry between the adsorbate and the adsorbent. Most of the time, the choice of an adsorbent, you be sure that there is no little or no chemistry between the adsorbent and the adsorbate. And then You have to also understand the surface chemistry, especially in cases whereby you want to reactivate the adsorbent. I mean, you want to reuse the adsorbent. So if you chose or the adsorbate you are trying to adsorb reacts with the adsorbent, in some cases the adsorbent may not be able you may not be able to reuse it. Okay, so you don't want it used up. So you have to study if you are absorbing gases or vapors, you have to understand the chemistry between the adsorbate and the adsorbent. Very important. Then the particle size. Okay, so um, when you have the smaller particle size, you are likely to have um, high pressure drops, and then the larger particle size may lead to low pressure drops. So depending on the design of your process, you have to understand the particle size of the adsorbate itself and the adsorbent. Okay, so all these factors out from the topics I gave you, some of you will still be speaking more on them, okay, from a practical point of view. Okay, so let's look at surface area more. Surface area more. So here is saying that, for instance, if we have a cube of sugar, you know, I said the larger the surface area, the more effective the adsorption process. Okay, so and possibly the faster the adsorption. Okay, so if you have a cube of sugar and then you break that cube into tinier cubes, okay, and you possibly pour let's say you break a single cube of sugar into about 30 smaller cubes. Okay, about 30 smaller cubes. So having 30 smaller cubes has offered a larger surface area to the adsorbate you are, okay, how do I put it? To the adsorbate you are trying to adsorb on that adsorbent. Okay, the cube of sugar now is the adsorbent. You have broken it down to offer a larger surface area. So the adsorbate, as it approaches the surface, can easily adhere, it can spread itself. And that's the concept between either using an horizontal column or vertical column. So you have to understand your process before you choose what type or design of your adsorption column. Okay, so I believe you understand that. So please, you can still read this after a while. So, and your surface area is equally related to the pore size. To the pore size, okay? So in instances whereby you have pore sizes, larger pore sizes, which lends a larger surface area. Larger pore sizes lending larger surface area, you have more effective adsorption processes. And in cases where you have smaller pore sizes, you can't still say, oh, I don't want a smaller pore size, because if the adsorbate you are trying to adsorb is of a larger size, you may desire a larger pore size. Okay, so the size of the adsorbate, okay, has also have a long way to go in choosing the type of adsorbent and then the surface area equally. So all of them, all the properties are kind of interwoven. You have to sit down with your team, decide, before you eventually decide on which process, okay, to go by. All right, so here you have the particle size of the adsorbents. Let me just remove this. This is talking about the mass transfer zone anyway. It's saying that if you have a smaller adsorbent particle size, you will have a larger mass transfer zone. It's just saying, like the example of the cube of sugar that I gave. if you have the spread of that cube, instead of having just 1 cube of sugar, you have the spread of about 30 cubes of sugar, broken down from that single cube of sugar. What happens? You have a larger particle size. You have smaller particle sizes, and that smaller particle sizes will enhance a higher mass transfer zone. It's called MTZ, mass transfer zone. Okay, so the smaller diameter of the pellet extrudates the bead, the granule, the less distance the contaminant molecule has to diffuse or travel to reach the adsorbent internal surface. I believe you understand that from our discussion so far. So it's just saying that if your particle size is small, then it has to travel, okay, a less distance. Okay, so because considering the pore, you are a petroleum engineer, so you understand pores in the reservoir and the flow of fluids, diffusivity, right? If you bring your knowledge of diffusivity into this course, okay? So when you have smaller particles in this wise, they are able to diffuse faster through the pores, depending also on the size of the pore, okay? So you desire that if you are choosing your pore size, you have to equally consider your particle size. That's the particle of your adsorbent. Okay. So when you have smaller pore sizes, they travel faster and you have more effective, okay, adsorption. Okay, then this last part, I've explained this before. The more external surface area there is, the more places the contaminant atom or molecule has to enter the adsorbent pore structure. Okay, so a larger, that's extensive surface area is equally effective, so it's equally effective. So you want to consider that before the choice of your of both your adsorbent, okay, of the process anyway. So let's look at the heat of adsorption. So generally, the heat of adsorption is the amount of energy that is released or absorbed when a gas or a liquid adsorbate interacts with a solid adsorbent surface. So the heat that is either released or absorbed. So in most cases, usually released. Okay. When your adsorbent is interacting with a hot process, I mean a process in which it is involved. For instance, you have a mixture of gases at a very high temperature, and then you want to adsorb particles of that gas on an adsorbent. So in such a case, you will have the adsorption of heat. Okay, energy will be released. You will have heat adsorbed on your adsorbent. Okay, so when molecules adsorb, they change to lower energy states because of the release of heat during the process. So just as you have the condensate, when a gas condenses to a liquid, okay, so you have lower energy as you have conversion from gas to liquid. Okay, so you have from a higher energy state to a lower energy state. So the greater the heat of adsorption of an atom or molecule, the lower energy state it is in after it adsorbs on the internal surface of the adsorbent. So if you have a very high heat of adsorption, then you have a lower energy state when the adsorbent will exist in a lower energy state when it adsorbs to the surface of your adsorbent. I hope you understand that. So the heat of adsorption is equally very important. For instance, when you have water molecules, they have a higher heat of adsorption. That is, because they have a higher heat of adsorption. Okay. Also depending on the process anyways. Okay. So when they have higher heat of adsorption, that is loss of heat, if it's coming at a very high temperature, okay, from the possibly from the inlet stream, what happens? As that heat of adsorption is lost, okay, so it begins to exist at a lower adsorbed energy state on the um adsorbent. Okay, as soon as it attaches to the surface or adheres to the surface of the adsorbent, it exists at a lower energy state because that heat of adsorption is lost. Okay, so this also depends on the process itself, on the design, the inlet streams, and then the outlet stream, the other process variables that are involved also within the units of that operation. Okay, so I know you've not done much of the unit operation, that's chemical engineering. If I were to speak to chemical engineers, they will understand some of the terms I'm using. I think some of you also took some courses in chemical engineering, so you should be able to relate because adsorption is more related to chemical engineering. But of course, some of you may still have to work, within the midstream. So you need the knowledge. Even in upstream, it's still equally, in a way, it's still applicable, especially when you have oil spillage and the like. So it's still applicable. Okay. So let's look at the adsorbent size more, density. Okay, let me just go to the porosity. Okay, I think this should be well understood, size and density. The porosity. So I think we've said something on porosity before now, but let me just reiterate that it's an indication of the internal structure of the adsorbent. Okay, it gives the value of fraction of the void space. I believe petroleum engineers, you understand what that means. The fraction of the void space of an adsorbent, either it's a pellet, um, a pellet on the granule, like some of the pictures I put up here. Okay. So, and some of you are equally familiar with what an adsorbent is. For those that buy shoes, you must have seen a small pack of something silica gel written on it. Has anybody seen that before?
Yes, ma'am.
Yes.
Yes,
Yeah.
ma'am.
Yeah, so
Yes,
you
ma'am.
see those small packs kept in your shoes. Okay. So what do you think that is for? Have you ever thought why those little packs are kept in your shoe packs?
It's used to extract moisture from the shoe for storage purposes so that it wouldn't have mold and the rest.
Okay, so you tried, but from the knowledge you've gained so far from this course, I believe you should be able to say it is an adsorbent, okay, which adsorb either water molecules, water molecules or vapor to prevent the formation of mold, like you said. Okay, so it just keeps your shoes, the shoes within the pack, it keeps them dry. It keeps them there because most of the time, these shoes and maybe some other things, they are transported in cool, very cool environment. Okay. For instance, you have maybe the AC running 24/7 or is transported via sea. Okay, so
Hello, ma'am. We can't hear you.
oh, can you hear me?
I can hear
We
you.
can hear you.
Yes.
Probably is his network.
Ah, it must be your network. Oh. Can others hear me?
I can hear you, ma'am.
Oh,
Yes,
Yes, we
ma'am.
can
We can
hear
hear you,
you
ma'am.
clearly.
fantastic. Okay, so the person that cannot hear me, can you hear me now? Can you hear me now? Okay, so please try work on your network. Is a whole lot, but we are trying to cope anyways. Okay, so the ease of adsorption, like I said, okay, I think we've treated this. Okay, we are on porosity. Porosity. Okay, we're on porosity. So I was talking about the pellets. So the pellets, for instance, silica gel, they absorb water moisture or vapor or yeah, water molecules, okay, that may want to settle within the leather of your shoes. And then it begins to, you know, it begins to either degrade or tear or swell or peel, or the sole may begin to peel. So in order to prevent that, those pellets are produced. They are adsorbents. Silica gel is an example of an adsorbent, so they are kept in shoes. So you have other types of adsorbents. So this silica gel is porous, and within the pore structure, you have the adsorption of water molecules. Okay, they adhere to it, and then some can stay as long as a year, 2 years, and then after a while, you discover that maybe the silica gel begin to swell, or sometimes it is used up. Sometimes you can't find anything in the small parts any longer. Sometimes it is used up. Okay. Sometimes it changes color. Changes color depends on the quality of production of the adsorbent as well. So the void space, that's the porosity of your adsorbent, its importance in its choice. Okay, so it's one of the physical characteristics of your adsorbent. So generally the density, the size, all these properties need to be considered. Okay, and you are not just considering the properties of your adsorbent only, you're also considering the properties, equal properties of your adsorbents and the process itself. You look at holistically. You also consider the processes involved within the units, okay, which the absorption is to be carried out. Your streams will come into play. The characteristics of your streams come into play. The process variables of that unit process itself, okay, also come into play. So all this, okay, are holistically being considered before choice is being made. So size and distribution, we have adsorbent with pores of between diameter pore less than 20, your 20A. You have the one mesopore between 20 and 500, the micropore greater than 500. Okay, so depending on the size distribution, this is equally important. And then you have times in which you have to mix the size distribution. Okay, so if you have to do a mix, or you have on different trays, you have, I think with my knowledge of chemical engineering, you can have different sizes on different trays. So as your inlet stream approaches, you know that the adsorbate from your inlet stream equally contains different sizes of the particles adsorbate particles, right? So as it approaches the first tray, sometimes the first tray is the first tray is the largest, the one with the largest, then it flows through, okay, and it goes to the next size, to the next size, to the next size, up to the least size. So sometimes you can have about 3, 4, 5 trays, and then the streams flow through them, and before you have the outlet flow, the adsorption would have been completed. So you can have the mix of different pores. You can have a single pore, and that is why I'll continue to say that the knowledge of the process and the streams equally important. So the pore size distribution may be determined by mercury porosity measurement. Okay, I think this is just an example. Okay, when you have adsorption, nitrogen adsorption, desorption measurement. Okay, so you can use the mercury porosity method to determine the size of the pores which will be loaded into the units. Okay, so that's an example. Okay, so here, let's look at percentage of pore volume and then pore diameter. You know what pore volume is. That's a fraction of your pore, okay, that your adsorbate can accumulate in from your porosity reservoir engineering sense, okay? Then your pore diameter. So I want you to unmute now. Okay, if you want to speak, you can unmute. So here I have zeolite. These are all examples of adsorbents. I have zeolite, I have silicone gel, I have activated carbon. They are all examples of adsorbents. Okay. From the topics book discussions I gave you, we'll still equally see. I believe you come up with more examples, and I have a feeling you're going to make it very interesting, and we're going to learn a lot. Okay, because I believe in you. Okay, so who can tell me about something about silica gel and the way it can behave um, in an adsorption process? Okay, so I'll give you 1 minute to look at it. So we have a pore diameter changing from 10 to 1,000, and it's showing pore volume. The pore volume. Okay. Here for zeolite, we have the pore diameter about 8, and we have the pore volume at about 98. Okay, that's about 98 point something. Let's say 98.5. Okay. And we have activated carbon changing pore diameters between 10 and over 10,000. So pore size distribution of different adsorbents.
Excuse me, is it
you
that we should
can,
explain this diagram?
so you can choose, yeah, that's what I'm about to say. I wanted you to study it first of all. Then you can choose to speak on any one of them and what you think their behavior will be in an adsorption process. Would you recommend them? Although depending on the process, which I'm not giving you now, but if you have an idea of the process you want to use it for, fine. But if you don't, just think of how any of these adsorbents will behave in an adsorption process. One, and then do you think you will recommend any of these adsorbents, okay, for any process? You can, for an adsorption process, you can give reasons. Okay, so let's go. Tell us your name.
Good morning, ma'am. My name is Akorodi Mohammed.
Okay.
Okay, so like you said, I don't really know much about the adsorption process, but I want to ask the question first now. That activated carbon, I believe that's also another name for activated charcoal, right?
Yes.
That activated the carbon there. Okay, so I can remember one time I was reading something online as on Twitter. So the post was talking about if someone mistakenly takes in poison, how activated charcoal can help in absorbing the poison. And if you look at the definition of absorption, it takes the adsorbent and sticks to the surface of the adsorbate. I mean, the adsorbate sticks to the surface of the adsorbent. So that's one practical use of activated charcoal, that's activated carbon here. And considering the from the graph here, the percentage of pore volume, we can see that when the volume is 0 here, the rate at which it's absorbed is not really high. Okay, it's practically 0, but as the pore volume goes up, the pore diameter of the activated carbon also increase almost exponentially with regards to the other to other pellets and silica gel. You can see that activated carbon does not absorb higher volume of substances compared to other absorbents here, but it has a higher pore diameter in terms of absorbing compared to others. I hope that's clear.
Okay, yeah, made a lot of sense. Well done. Fantastic. Okay. What's your name? Your name again, please.
Akorede Mohammed, ma.
Okay. Mhm.
Hello, ma.
Go on, please. Your name.
Yes. Please, I would just like to try with silica gel.
Your name.
Olasukomi address. Guys. Okay. So silica gel basically, as we know, is used mostly, we see them in shoes and most of the times, one of the reasons why I think they are really used in as an absorbent in that scenario, right, is because of they have less micropores and larger what's it called again? So their micropores is a bit smaller, right? And because of how they are coagulated in the pack, right? So it allows for effective moisture control. So effectively trapping the moisture in whatever surrounding it is, right? So, and because of that, it helps to absorb the water in the moisture effectively, right? So you can easily trap it in that particular scenario. And I think it's a whole lot more versatile in that particular area compared to using activated charcoal because like Korede just said just now, when you look at activated charcoal in the aspect of poison and all of this, yes, activated charcoal, they can exist also in our environment. When you put both of them together, you find out that because of the pores of silica gel in comparison with the pores of activated charcoal, silica gel has the ability to hold more moisture content compared to activated charcoal whilst being used in its own. Did you get that one?
Okay. Yeah, fantastic. Well done. Okay. Yes, more contributions.
Good morning, ma.
Yeah, good morning.
Adejola Muiz.
Okay, Adejo.
I want to speak on silica gel, ma.
Okay, go on.
Okay. So, according to what I know, silica gel has a high porosity. It has a large network of pores, which also, according to what you said a larger pore size also relates directly to larger surface area. So in the graph here, the large pore volume, although it is not as large as the zeolite, but then it also makes adsorption easier and faster because the internal surface area determines the power and speed of the adsorbent. Also, silica gel aids with water molecule attraction. And when water molecules come in contact with the silica gel, they are drawn to the adsorbent, which is the surface of the silica gel, and they adhere to the surface, which, according to what you said, which reduces the risks of tears or the leathers not tears are moist, and also silica gel is is primarily used for water vapor adsorption, according to my knowledge, because in shoes and other pharmaceutical stores and shoes and other ways where we use it, it is mainly to absorb the water molecules to keep them dry and stable.
Okay, fantastic. Well done, Adejola. Okay, yes, more contributions.
Hello, good morning.
Hello,
Good
ma'am.
afternoon, ma'am.
On zeolite, equally
Good
speak
morning,
up.
ma'am.
Good morning,
Yeah,
ma'am.
let me take the lady.
Okay,
I
good
three
morning, ma'am.
guys
My
are
name is
for now. Your name is?
Oluwayemisi, ma'am.
All right, Oluwayemisi, go on.
Okay, so ma'am, I want to give a try on the zeolite 5A crystal. So, from my knowledge, yeah, from the diagram, I mean, from the graph here, the percentage of the pore volume is very, very high, which is a good cause. But looking at the diameter is not so high, and with that, I think it is not a good option. From my knowledge, actually, if I'm going to be recommending any of these absorbents, it's going to be silica gel, because there is no use of the percentage being high, and it can't okay, yes, there's no use of the percentage being high, whereas it cannot absorb as much, it can't absorb very much. So I think one of the uses of the zeolite is used for removing water and sulfur from soil natural gas stream. So yes, ma'am. So what I just want to say is that if I'm going to be recommending any of these absorbents, it will probably be silica gel, ma'am. Thank
Okay.
you, ma'am.
Anyway, yeah, well done. Fantastic. Anyway, also depending on the process.
Sorry, ma.
Okay,
I want to
more
ask something, ma.
contributions on zeolite. Don't ask questions. More contributions on
No, I just
zeolite.
want, it's like contribution, ma.
Okay, go on.
Ma, can we also call silica gel like a drying agent? Can it qualify as a drying agent?
You said it's a contribution, not a question.
Sorry, ma.
Yes, it is a drying agent.
Okay, that's what I want to know, ma. Thank you, ma.
Contributions, please.
Hello, ma.
Yes, go on.
So from the graph, as we can see, zeolite has a high percentage pore volume, which means that its rate of adsorption is very high, but its pore diameter is very low, which means that effectively the amount of adsorbate it can absorb is small compared to silica gel, which has a relatively high percentage pore volume, which means that its rate of absorption is also high, and its pore diameter is large, showing that it can absorb a large amount of adsorbate. While you see the activated carbon has a relatively small percentage pore volume, which means that its rate of absorption is lower than the others, but it has the highest pore diameter, which shows that it can hold the highest amount of adsorbate here. So if you're looking at an advice for use in the industry, zeolites should be used in areas with low amount of adsorbate. That's the adsorbate content. What you want to absorb is very low, and you want to get the job done very quickly. Silica gel could be used in places where you have a high adsorbate. That's high amount of adsorbate, and for efficiency, you can store large amount of adsorbate. So that's a very good option. While activated carbon should be used in places with low amounts of adsorbate, as the rate of efficiency of absorbing those adsorbate is low, but it can store a large amount of those adsorbate.
Okay. So let me ask a question now. Do you think this zeolite has any disadvantage?
The storage capacity, man. The amount
think deeply before you answer.
Sorry, could you say that again?
Take a moment to think before answering.
Okay.
And anybody can answer the question.
Ma, can I try?
Yes, please do. What's your name?
Sabata.
Okay, please hold on. Who spoke before now? Before Sabata, please. Who's the last person that spoke? What's your name?
Edward Divema.
Edward.
Yes, ma'am.
Okay. All right. Go on. Go on, Sabata.
Okay, so picking from the YouTube video that you first showed us, I could tell that first those balls were zeolites, and from it I can say that the pore diameter, like the zeolites can only let absorbates that are only smaller than the pore diameter. I think that is a disadvantage for it. So I would say that it has selective adsorption.
Fantastic. Fantastic. I was actually looking out for that. That's why I asked the question, because I wanted you to be able to compare the variations that activated carbon pore diameters offers compared to that of silicone gel and compared to that of zeolite. So in what type of process, another person now, would you
Can I ask a question?
I'm taking contributions now. Just hold on with your questions. Okay. So in what type of process, adsorption process? So my what type now is kind of relative, but I don't want to give a statement that would depict the answer straight away. So in what type of process would you recommend zeolite for? Adsorption process, I mean. Can anybody hear me?
Yes, ma'am, we can hear you, ma'am.
All right, thank you. So anybody want to take a shot at the question? I'm waiting. Okay. Okay, while you are trying to put your answers together on the question, if you have
Well, can I
other
try?
contributions, okay, all right. What's your name?
John Onuzomo.
John. John what?
Onuzo. John Onuzo.
Okay, go on.
Yes, ma'am. I see. Zeolites from their pore diameter here, they are excellent and best for absorbing gases. And more like used for like gas purification and separation.
Okay. I'm thinking you got that from online because gas is not indicated in this chart. I want you to speak basically on what you can see on this chart.
Okay, can I go on? Can I
Go
say
on, please. Your name?
Kuredima. Kuredima. Okay, so like what Sabata said, effective absorption. To add to that, Maurice, can you hear me?
Yeah, go on.
Okay, to add to that, I'd say zeolite would be best for absorbing substances that are very, very tiny. After you've used maybe silica gel or activated carbon to absorb majorly most of the impurities, if you are undergoing a kind of separation process, most of the impurities here. So the tiny ones, that are very, very tiny, that silica gel and activated carbon might not be able to capture. That is where zeolite would likely come in. Why? Because it has a very high volume, high percentage of pore volume, and if you look at the pore diameter, is very, 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 very small. So that's just my idea.
Okay, fantastic. Yeah, you're right. And Sabata was equally close to the answer as well. So you will have particle sizes that are smaller than the pore diameter of the zeolite. Okay, so the disadvantage is if you have a stream of adsorbates of varying sizes, the zeolite may not be applicable. Okay, you may be looking at time, you may be looking at profits, you may be looking at energy. All these things will have to come into play. If all the particle sizes of your stream is less than the zeolite, the pore diameter of the zeolite you are considering, then fine, that would be fantastic. But if you have variations in particle sizes, okay, especially the ones that are far larger than that of the zeolite you are considering, then it won't be at your advantage. So I also expected responses in terms of variation in the pore diameters of activated carbon, which is a big advantage, a big thumbs up to activated carbon because, yeah, the pore volume may be low, but it's saying that at even pore diameter, even lesser than, it can offer a pore diameter that is even lesser than the zeolite, and you can still have a bit of, though still very close to zero. Here, close to 10, okay, close to 10, you can still have a measure of adsorption, and then as it goes up to 10,000, though as the pore diameter further increases, what happens? The percentage volume, depending on the process, okay, the percentage volume drops. Okay, so it's used up gradually. Okay, and one of the reasons why you can have a drop in the pore volume, okay, as this increases, is because the surface area, okay, surface area is used up faster. So you have lesser pore volume as the pore diameter increases. Okay, so silica gel is a fantastic one, though it has its pore diameter window between 10 and a bit above 100, that's about 120. So it has the window, it's fantastic. So if it goes outside this window, what happens? You have a poor percentage volume, poor volume, okay, which lends itself to adsorption. That's the space in which your adsorbate is actually accumulated. Okay, so it's poor when it goes out of this window, out of this silica gel, this fantastic window, okay, between 10 about 120. Oh, sorry, this is not 120, this is about this is 100, is 1,000. This is probably about let's say 200 or 300. Okay, so I hope we've been able to learn a lot today, especially from this chart. We have seen that pore volume property, pore diameter property, like I said, they cannot be considered standalone. You have to look at them all together. All the properties are actually integrated. So you have to consider them all together before making your final decision on what to use. Yeah. Any question? I hope I can answer your question. Any question? Any question? Someone wanted to ask a question the other time. Let's have it. I hope I can answer. Go on.
I think you've answered it.
Oh, okay. Fantastic. I love that. Thank you for listening.
Good morning, ma.
Yeah, good morning.
Good morning, ma. Yeah. My name is Ian Olua, and I want you to shed more light on the absorbent porosity. There's actually a particular equation there that is kind of not clear to me.
Okay. Where?
Under adsorbent porosity. Yeah.
Okay. So read it out.
So the equation which says that Vpor is EP over rho P. So I'm trying to understand how the Vpor, which is the pore volume per unit absorbed mass,
This is the pore volume.
right? How,
And it's your specific pore volume over what? Pore volume per unit adsorbed mass.
yeah, but our foundational knowledge under porosity says that porosity is the percentage ratio between the volume of the void over total volume. So I'm now trying to understand and relate how the absorbed mass relates with the total volume of the adsorbent.
Okay. You know, in the case of your reservoir engineering, there is no adsorption, right? You only have the filling of your pore volume with what? With your reservoir fluid. Do you get it? So in that case, there is no adsorption. But here, we are considering absorption. So why pore volume per unit adsorbed mass? Because that is what can be measured. We'll still get to, I think, under Beth's isotherm, we'll discuss more on that. Because actually from when isotherms were being developed, the unit adsorbed mass was used because they couldn't quantify what happens over a large mass of adsorbent. So a unit adsorbed mass was used in quantifying the volume of the pore. Do you get it? So it's the specific pore volume of the adsorbent, okay? The ratio to the unit adsorbed mass. So if you have, for instance, using your activated charcoal, so a fraction of that activated charcoal will be used instead of taking a large mass of measurements. So a fraction will be used. And I think it's also one of the shortcomings of some of these isotherms. When we get to isotherms, you will understand further. Okay, shortcomings, but most of the time it is being considered as an uncertainty. So when they did consider the per unit adsorbed mass, that is a specific mass, they now, use it, that becomes a multiplying factor over a large mass of adsorbent. So Yeah, you can apply the knowledge of your reservoir, but in terms of reservoir, and also even in your reservoir engineering, you consider I don't know, when under your development of your diffusivity equation, you consider the Q. Did you do that? I don't know, maybe the course is in 500 level or your 400 level, 400 level first semester. You consider a Q. You consider a Q, and then you begin to uh, develop your diffusivity equation step by step. So that single Q, okay, is then multiplied. For some of you that have been using Eclipse for development of the static reservoir model, okay, nobody can say, okay, we were able to develop a model based on the whole volume of that mass of that reservoir. Yeah, but some points are taken, different points are taken within the reservoir system, and then it is multiplied. Okay, so there are uncertainties that are, related to some of these models and calculations, but they are just uncertainties. But over time, they are being used. Even if errors are attached, the errors are quite minimal, although there are cases whereby there have been costly decisions anyway. But over time, they've been able to make adjustments. Well, for those that did, that did their IT in reservoir engineering specific units, they will understand some of these things I'm saying. So what I'm saying in essence is that you take a small mass, a unit mass of a system, you can take it at different points and then multiply it over to determine whatever you are trying to calculate over the large system. Even in statistics, if you have to determine over 100,000, let's say, specimen, you can take in hundreds or in 50s, then you take a sample in each, and then that becomes your determining, factor. I don't know if you understand what I'm trying to say. So what this is saying in essence is that your per unit adsorbed mass, the pore volume is taken per unit adsorbed mass. Okay, that's how it is measured, because there is an adsorption that takes place, okay, in that pore volume. When you're in your petroleum engineering, you have production, right? Am
Yes, ma'am.
I able to speak to what you've asked?
Yeah, let me try to understand you, man. So you say that since in the case of activated charcoal, that the old surface area is not being used up, we tend to focus on
I
the
did
part
not
that is
say
being used up.
it's not being used up. That is not what I said. I did not say it's not being used up. I said a unit absorbed mass is used in making, in quantifying or in the calculation. Do you get it?
Okay.
Yes.
Yeah.
A unit is used. By this time in your 500 level as an engineer, you should understand when someone says a unit mass is used, yeah, in the calculations, and then can be multiplied over a large mass. But the unit
Okay.
mass may not be taken in just one point, can be taken at different points. That's why you have pore volume per unit adsorbed mass.
Okay.
Do you get it?
Yes, I do, man. Thank you
I'll
very much.
encourage you to equally still read more, and then you can have a better understanding.
Thank you.
Okay, this is almost 12. Let's look at this. You have your adsorbent size, the activated carbon, the silica gel, activated aluminum, and the zeolite. You have their densities. Here we see that the zeolite has the largest density so far. You have the porosity. Activated aluminum having about 0.5 to 0.77. Your carbon 0.4 to 0.7, which is good. Your zeolite, which we have seen, is 0.2 to 0.5. Then the specific surface area which they lend, your carbon ranges between 200 to 2000, which is the highest so far. And then followed by the silica gel, and followed by zeolite, and then the aluminum. Okay, then the pore size, your activated carbon, 1600 micropore. So that about 2 to 4 mean micropore. Then you have your silica gel between 1 to 40, your activated aluminum between 1 to 8, and then your zeolite between 2 to 10, which is kind of the smallest. Okay. So let
Hello,
me.
sorry, ma.
Yes.
Please, I have a question about that previous chart and the other diagram.
Okay.
So there's no column for their let me just say absorbing properties. Now, their absorbing properties, are they like just directly proportional to the figures you have in that other table?
You know, the
And then
adsorption properties all depends on the density, the porosity, the specific surface area, the pore size. They are dependent. I won't say directly, but dependent on all the adsorbent properties. Okay? The adsorption capacity depends on the adsorbent property. So depending on the size, depending on the density, depending on the porosity, depends equally on the surface area, the pore size, and as many properties that you can still find in literature. Okay, so you can't expect zeolites that have 1,100 kilogram per meter cube density to behave the same way as your activated carbon, which is between 500 to 900, though it's quite loose. They are all quite loose, okay? But in terms of the porosity, 0.4, 0.7 won't behave the same way as between 0.2 to 0.5. Okay.
All right, so their behavior is like more on the type of the material than, or can you like straightforward explain the trend in terms of absorbing properties, or it just depends on the type of the absorbent material?
It depends on the process. I've said this over and over. Their behavior will depend on the process. If you are using activated carbon in absorbing a gas, how it will behave, it will depend on the process, will depend on the adsorbents from the gas system. Okay? But when we get to isotents, you will understand some of this behavior. Do you get it?
Yes, ma'am.
I have an observation.
Okay.
So looking at this table, there's the adsorbent size, there's the density,
there's porosity, there's surface area, there's pore size. And looking back at the chart, we have pore volume, percentage pore volume to pore diameter. Is it safe to say that the mass volume relationship of density can be employed in finding the missing components?
What's missing component?
Like the pore diameter, the diameter, yeah, the pore diameter.
Yeah, but the pore diameter is on the chart.
Yeah, I'm just trying to look back at the table and say, like, before we plot the charts, we need to have a table. So I'm just trying to think about it, like, when constructing a table,
You can
and trying to derive.
you can Google up the pore diameters of the varying pore diameters which all these adsorbents can lend. Okay, depending on the
Okay, somebody
manufacturer.
has done it.
Yeah, they equally manufacture based on the process. Maybe request from the industry that they want this size of pore diameter. Okay, because they are probably intending to absorb a certain window, size of adsorbate. So they can also can be application specific. Do you get it?
Okay.
Yeah.
Okay, the adsorbate size determines the diameter.
Yes,
Like, I'm trying to understand what you mean.
yes, adsorbent size can determine the diameter. And if you have varying diameters in the adsorbent producing industry, so you know the diameter that you need. Do you get it? And then you place your request. Oh, we need so diameter. I think there is okay. Let me show you this. Do I have? Okay, looking at this now, this activated charcoal. Do you think they have the same diameter?
No.
Yeah.
Obviously, one is small and one is
Yeah.
big.
Yeah. So don't box yourself. Don't put yourself in a box. You have varying diameters, and you can make recommendations based on the process or based on the adsorbate you are intending to work with. Do you get it? If you check
That's nice. Yeah.
if you check some other illustrations on the internet, you will see the molecular sieves, you will see the silica gel in varying sizes, depending on the mesh size. Some are very tiny, very small. Some are quite big. Even your silica gel, if you open up different silica gel, all those pellets in your shoes, you will see some, they are varying sizes. In fact, in some packs, you can find like 3, 4 sizes packed together.
Yeah, that's right.
Okay, so you have the activated alumina. Oh, okay, this was actually the picture I was looking for to illustrate your question. Can you see here? You have the
Yes.
activated alumina. So you have different sizes.
Okay.
If you Google up pictures with different sizes on the internet, you will see some pictures where they are to be loaded into different units of varying sizes. Okay. So for your activated alumina, this is an example of I think we have seen it before of an adsorbent. Okay, formed from dehydration of colored alumina or bauxite. This is a specific surface area. It can be regenerated by dehydration and reused. And that's one of the desirable properties of adsorbents when they can be reused. Okay, it's quite desirable. So if you are not used up in the first process, oh, fantastic, you want to go for them. Okay, then has superior mechanical strength, especially in moving bed applications, high adsorption capacity for water vapor and the hydroxyl group, then can be used as desiccant for gases and liquids. Then you have your silica gel, activated silica. Okay, so if you look closely at this picture, I think this is just a single diameter. Yeah, this of equal diameter. Okay, I can see the, okay, so it's of single diameter. So prepared from gel precipitated by acid treatment of sodium silicate solution, used primarily for dehydration of hair, removing toxic species from hair for personal protection purposes, using gas masks as well. Surface area of silica gel is hydrophilic, that is water loving, and commonly used for drying gases, and also applies where there is requirement to remove unsaturated hydrocarbons. It's brittle and may be shattered, so you have to handle that, to be well handled with care. Okay, this is also silica gel. So tougher varieties are also available with slightly lower surface area. So it can come in varying surface area. I believe you can see that now. Best known absorbents, which is small sachets of gel, packages of material that might deteriorate in a damp atmosphere. Okay, like maybe goods transported over the waters. So you can, in a very damp atmosphere, it changes color. Okay, so sometimes a dye is added in manufacturing process so that the gel changes color. When it changes color or becomes saturated. And this is molecular sieve. They are crystalline or inorganic polymers of aluminosilicates, alkali or alkali earth elements like sodium, potassium, and calcium. So they have cages. That's one beautiful thing about molecular sieves. They have cages of crystal cells, can entrap, absorb matter, and the diameter of the passageways controlled by crystal composition. Okay, they regulate the size of the molecules that can enter. Okay, so they also possess lattice structure. You can see the structure here. There are more elaborate diagrams on the internet. You can please pull them up. Please don't just rely on the slide I'm giving you. I can't put everything in the slide. As much as I want to, I can't put everything in the slide. So I expect that you go back, please watch videos, read more. Yeah, so the lattice structures of molecular sieves are composed of tetrahedra of silica alumina arranged in various ways. Okay, so gives them an added advantage. Okay, I think this is the link to the video I was trying to play the other time. So we can copy and watch. I'll still update the slide with more links. So this is also talking about the molecular sieves. They have cage-like structures. They have windows that can admit only molecular size less than a certain size, like we saw in the graph I showed us before, that profile that shows porosity is a pore volume against the pore diameter. Remember, okay, so zeolite. It is possible to produce a range of molecular sieves with access dimensions of 0.3 to 1 nanometer. I believe this answers somebody's question that, okay, is there a specific size? No, yeah. But if the highest size which that adsorbent can accommodate is, for instance, 1 nanometer, for example, then the industry could possibly produce sizes lower than that. okay, so that it can accommodate size of adsorbate, okay, that falls within the range, and then it can be effective for the process, okay. So the dimensions are precise for a particular seal because they derive from the crystal structure of that seal. So please, you can equally read up the rest. There are interesting things about each of the adsorbents. This is activated carbon, and you can see here the one in this container or spoon, or what do I call it now? The size is quite smaller than the one on the background. Okay, so it can lend, there's variation in pore sizes. Okay, so activated carbon produced from carbonization of natural occurring carbonation materials such as coconut shell, coal, lignite, wood bones, shells, and similar substances. Some of you will be working on activated carbon, I believe. I know many chemical engineering projects deals with activated carbon because they do more of adsorption anyways. So they try to even integrate materials of different materials together to study the effectiveness of adsorption, perhaps possibly the adsorption rate, you know. So activated carbon from wide um, material, source of material, coconut shells, coal, lignite, wood, bones, shells, and other similar substances, followed by activation with air or steam in an inlet atmosphere at a temperature of about 800 K. So very high temperatures. They are burnt under very high temperatures. So they are widely used for recovery of organic vapor, decolorizing liquid solutions, treatment and purification of water supplies, and wastewater. I think there is a topic I gave you that has to do with water. Please, the group should kindly do due diligence. If you are choosing activated carbon, we want to see possibly a live process. Maybe you take a short video and then show to us. It will boost your presentation. Because the product will not be porous, it needs additional treatment or activation to generate a system of fine pores. The carbon may be produced in the activated state by treating raw materials with chemicals such as zinc chloride or phosphoric acid before carbonizing. Okay, so I want you to read up more on the formation of some of these adsorbents, their properties. You have not yet in this slide, so please read up more on them. Okay, so here we see activated carbon, the pore radius and the pore volume versus pore radius for liquid phase process. Okay, so here there are 3 different activated carbon, okay, being used of different sizes. Okay, so being used for a liquid phase process, like I said, is most of the time is process dependent. Okay, so here we have the darker profile or the trend, the darker trend over 1 to 10,000. You have the pore volume, the pore radius between 1 to over 1,000. Okay, you can see the pore volume, the variation of the pore volume. Then the one in the middle, okay, you can see it has a higher pore volume at about 10 radius. And then the last one also showing variations. Okay, the middle one, you can see it has the highest pore volume, even at a very at a lower pore radius, okay, compared to the second and the third. Okay, so what this shows you is that when it comes to adsorption, you can have variations depending on the process, depending on the size, okay? Depending on the size. I possibly presume this is from somebody's work anyway, so we can't really tell what exactly happened. But this is just showing that trends can differ. But I want to presume that the one in the middle probably is of a um, smaller pore size. Yeah, smaller pore size. Of course, yeah, the pore radius smaller, and then is lending itself a larger pore volume. Okay, so and these are from different raw materials. So we can't tell whether this is from shell or this is from coal, lignite, wood. Their behaviors also differ. Okay, so whether you produce your activated carbon from shell, from wood, these are some experiments that students in chemical engineering actually perform. So you can tell. So you see that there has been a question on I think on size. Yeah, on size. So you have seen that it is not just size, even the source or the source from which your adsorbent is produced from is also a major factor that determines the effectiveness of that adsorbent. Okay, so possibly this is produced from maybe from coal, maybe the one from coal at lower pore radius offers a higher pore volume, or the one from shell. Okay, coal, shell, lignite, the one from wood, or the activated carbon from bones. Okay, so the source from which it was produced from also affects its effectiveness. So activated carbon used in treating water as a powder, in which form it is mixed with liquid to be treated and then removed by filtration. So what is saying that in powdery form, it can be used in treating liquids in powdery form and then removed. Okay. It is economically to regenerate. Granular carbon is normally regenerated after use, okay, because it has low affinity for water. So these are reasons why activated carbon is desirable. By carefully choosing starting material and the activating process, like I always say, the process, okay, it has been possible in recent years to generate in carbon a pore system with a narrow span of pore sizes. So this is, I believe, is from the industry that produces activated carbon over the years. They also have done their research and discovered that, oh, activated carbon can come in span that is varying pore sizes, and it will be applicable to varying processes depending on the desired pore size, the desired pore size based on the process to be used for. Okay, so and we have polymeric adsorbents prepared from styrene, divine benzene, other acrylic esters for absorbing non-polar organics, okay, from aqueous solution or polar solutes. Okay, so this can possibly be used for on the waters where we have oil spillage. So they can absorb oil molecules, okay? Polymeric adsorbents are more expensive than other adsorbents, and their use is therefore more selective. So they are you can only recommend it when you understand the process that you use it for. Okay, so I believe we have a basic understanding of what adsorbents and different types of adsorbents are, how they can behave, okay, and then their applications. These are the applications. We said few things about them. You can read up the slides. They are quite understandable. Where you can use silica gel for drying, activated alumina, where you can use your carbon, okay, your zeolite, where it is applicable, your polymers and resins, where they are applicable. Please look at them all, okay? So generally, to be attractive commercially, an adsorbent should embody a number of features. It should have large internal surface area. Of course, from our discussion so far, the internal surface area, oh, I was thinking it's past 12 already. Okay, so the internal surface area is desirable. The area should be accessible through pores big enough to admit the molecules to be adsorbed, of course, from all our discussions so far. The adsorbent should be capable of being easily regenerated. Yeah, we have mentioned that over and over. The adsorbent should not age rapidly. This would be a desirable property. If it does not age rapidly, of course, you're saving your company some cash, okay? So doing your due diligence by understanding the process holistically would help. Okay, so if it doesn't age rapidly, for instance, maybe you are making use of your activated carbon, which you can always regenerate. Maybe not even regenerating. After use, you can easily gather it up again and then reuse and reuse. It doesn't age rapidly, so it doesn't get used up rapidly. Okay. Then it is mechanically strong. It can withstand bulk handling. It's not brittle. They are adsorbent that can easily crumble, does not easily crumble, can withstand vibrations. If you have vibration within your system, columns, it can withstand the vibration, it can withstand pressure, temperature, and all that. So there are features to be considered while choosing adsorbent. So this is also like a summary. Factors affecting adsorption of gases by solid: adsorption area, the nature of the gas, the heat of adsorption, we said something about that, reversible character of the solid, the effect of temperature on the solid. Okay, if your inlet gas is at a very high temperature, what effect will it have on your adsorption solid? Okay, effect of pressure on the adsorption solid. Like we said, desirable characters of these adsorbents that they should be able to withstand these process conditions. Thickness of adsorbed layer of the gas. So when we have multi-layer adsorption, can your salt adsorbent withstand multi-layer adsorption? Okay, so when you have several layers of molecules of gas being adsorbed on your on the surface of your adsorbent, can it withstand it? Okay, so we don't have time to go through this. We'll look more into this next week. I would have loved that we also look at this, but our time is fast spent now. But from all our discussions today, I believe this should be a walkover. Here you have relative humidity and you have water molecules. You have water molecule by solid. Kilogram of water molecule by solid. Okay, I hope I can see that. Yeah, by solid. So you have the behavior of your silica gel, the behavior of your aluminum. This is actually from somebody's work. Okay, so the behavior of alumina, carbon, silica gel, zeolite. Okay, in the presence of, as relative humidity increases, how does your silica gel behaves? How does your carbon behaves? Your activated carbon. You can see kilogram of water, okay, quite low. That of alumina is quite high, okay, relatively humidity increases. Okay, so these are isotherms. We are going to isotherms next week. So these are isotherms. These are isotherms. So you understand each of these isotherms better by the time we get to isotherms, okay? Yeah, so we'll stop here. Please, I want to beg of you to read your slide and equally read other materials. Please do. Please do. Okay, so contribution, if there are questions, that may be next week. You can send them to me privately. And then your group work, please, you have your groups and your topics. Try as much as possible to kickstart a discussion with your group members. Is there any group member that is not cooperating? Just send the matric number and the name of the person to me. Just, you have my contact, and you can get my phone number from your class rep. Please send the number of the person and the matric number to me. All right, so I wish you all the best. Please, I want to see your post on LinkedIn. You are not just
Sorry, Ma.
Yes.
My name appears on 2 groups.
Your LinkedIn.
My name is on 2 groups.
Oh yeah, I've updated the grouping, so I will send the updated version to your classroom. What's your name?
Okay. Praise.
Praise, okay. No problem, that has been sorted. So if your name appeared twice, it has been sorted. Or
Okay.
I'm only waiting for comments from your class reps and assistant class reps as touching maybe names of those that do not appear. If there are people on this call that are extra year students or students from taking this course as an elective, please reach out to the class rep so that I can put you into group. Do we have students from chemical engineering on this call? Do we have them taking this course? Sabata, Jackson.
Ma, for now, there's no chemical engineering students on this
Okay,
course.
all right, fantastic then. So I believe, I think about 58 students taking this course, and I have about 45 students at the very beginning of this class. So I don't know why the remaining 10 or 15 thereabouts are not joining the call. All right, so that will be all for today. I hope you've learned something new. I hope you go back to read. I encourage you to please do so. Go back to read. I can only put few things on the slide. Please, I'll also send the notes to you so that you can read up. All right, so that'll be all for today. Any comments, any question? Okay, so that'll be all for today. Thank you, everyone. Bye.
Bye, ma. Thank you, ma.
Yeah.
Bye, ma.
Bye.
Good, thank you, ma.
All right, bye.
Thank you very much, man.
Thank